Welcome to a video on magnetic and electric fields. We'll first discuss magnetic fields and inductors. You're certainly familiar with magnets. These produce magnetic fields. Current-carrying wires also produce magnetic fields. These are about the wires and flow in an anti-clockwise manner when viewed looking back down the wire. Give yourself a thumbs up. If your thumb is the wire and the way it's pointing is the direction of current flow, your four fingers point in the direction of the magnetic field curves around the wire. We'll call these individual curves Amperian loops. An important piece of terminology here is flux. All this means is the amount of something passing through a surface. Because it gets complicated trying to picture field lines through three-dimensional space, we choose to analyze them as lines passing through a plane, so as points on a plane. We can then describe properties of the flux, such as its density. So when we say magnetic flux, what we are describing is the flow of the magnetic field in space. Getting back to wires, not only do current-carrying wires produce magnetic fields, but a man by the name of Ampere discovered that the flux density at a point about the wire, so the strength of the magnetic field at that point, is directly proportional to the current in the wire and inversely proportional to its distance from the wire. If we combine these two relationships, we get Ampere's law, the magnetic flux B equating to mu naught divided by 2 pi multiplied by the current divided by the radius of the Amperian loop. In the proportionality constant here, we have a universal constant mu naught, which is called the permeability of free space. We now know the flux density at a given point. To find the total magnetic field, we can integrate around the magnetic field line, the Amperian loop, which in this case is a circle. This equates to the permeability of free space multiplied by the current. Here, dl represents all the infinitesimally small sections of the loop. Note that this is a finite integral as denoted by the circle. While B denotes the magnetic field density, the strength of the magnetic field is termed H. The distinction between these two lies in the complications that arise when generated magnetic fields pass through magnetic materials, which themselves contribute internal magnetic fields. H unambiguously designates the driving magnetic influence from external currents in a material independent of the material's magnetic response. H equals B divided by the permeability of free space times the relative permeability of the material. If the material does not respond to the external magnetic field by producing magnetization, then the relative permeability is equal to 1. If the material is ferromagnetic, however, this value may be much higher. We'll now take a look at the internal and external magnetic fields about a wire. Internally, we consider an Amperian loop wholly within the wire circumference. We first write our equation for the B field around the loop. Next, we determine that we are integrating around a circle, so the sum of our dl's will equal 2 pi times the radius. Before we write our equation for the current within this area, we assert that the current is distributed uniformly across the entire cross-section of the wire. Therefore, our enclosed current is I multiplied by pi small r squared over pi times big R squared, where big R is the radius of the wire. Substituting, we find our overall equation for the magnetic field B. Externally, we consider an Amperian loop outside the wire's circumference. Our equation about the Amperian loop remains the same, and because now our enclosed current is identical to the current in the wire, the equation for the magnetic field B is mu naught multiplied by the current, all divided by 2 times pi times the radius.